Imagine for a moment that you're sitting in your favorite chair, sipping your coffee, and then, poof, everything around you just vanishes. Not just the furniture or the walls, but the air, the light, even the very fabric of space itself. What if everything in the universe disappeared? It sounds like a scene from a sci-fi movie, right? But what if this wasn't just fiction? What if it was a real possibility that scientists have been quietly pondering for decades? This is where we dive into the mind-bending world of the vacuum catastrophe, a concept so strange and counterintuitive that it might make your head spin. It's not about aliens or time travel, but something even more fundamental: the very emptiness of space. The universe, as we know it, isn't actually empty. In fact, it's filled with a kind of energy called vacuum energy, which is thought to be the source of dark energy and the mysterious force driving the universe's expansion. But here's where things get weird. Quantum physics tells us that even in what we think of as empty space, there are constant fluctuations. Tiny particles popping in and out of existence like popcorn in a microwave. These fluctuations create an energy density that should be incredibly high, but when scientists try to calculate it using the equations of quantum field theory, they get a number that's way too big compared to what we observe in reality. This discrepancy is known as the vacuum catastrophe, and it's one of the biggest mysteries in modern physics. So why does this matter? Well, if you think about it, the vacuum catastrophe isn't just an abstract problem for physicists. It has real implications for our understanding of the universe. If the energy density of empty space is so much higher than we can measure, then that means there's something fundamentally wrong with our current theories. It could mean that our models of quantum mechanics and general relativity are incomplete or even incorrect. And if those theories are wrong, then everything we think we know about how the universe works might be a complete illusion. But don't worry, this isn't the end of the world, yet. In fact, it's an opportunity to rethink everything from the smallest particles to the largest galaxies. Now, you might be thinking, okay, but what does this have to do with me? Well, if we can't figure out why the vacuum catastrophe exists, then we might never fully understand the nature of dark energy or how the universe will evolve in the future. And that's a problem because dark energy is already causing the universe to expand at an accelerating rate. If our calculations are off by such a huge margin, then maybe the fate of the cosmos isn't as clear-cut as we think. It could be that the universe ends in a big rip, where everything is torn apart by the increasing expansion, or it might collapse into a big crunch if the energy density is high enough to reverse the expansion. Either way, the vacuum catastrophe is a reminder that even the emptiest parts of space are anything but empty. So, as we move forward in this video, we're going to explore what exactly causes this discrepancy between theory and observation. We'll look at how quantum field theory predicts such an enormous energy density, why our measurements don't match up, and what some scientists think might be the solution. It's a journey into the heart of one of the most perplexing problems in physics, one that challenges not just our understanding of reality, but our very sense of what it means to exist. And who knows, maybe by the end of this video, you'll start seeing the universe in a whole new light. So, you've heard about the vacuum catastrophe, but what does that even mean? Well, imagine if you could somehow empty out all the air from a room and then magically remove every single particle of matter, like everything. That's what physicists call a vacuum, right? But here's the twist. Even in this perfect emptiness, there's still something going on. Turns out that empty space isn't really empty at all. It's full of energy, and that's where the catastrophe comes in. The vacuum catastrophe is basically a big problem in physics that has to do with how we understand the energy of empty space. You see, quantum mechanics tells us that even when there are no particles around, there's still a lot going on at the smallest scales. Tiny particles called virtual particles pop in and out of existence all the time, like little ghosts of the universe. These particles borrow energy from the vacuum for a split second before disappearing again. But here's where things get weird. When physicists try to calculate how much energy is actually stored in this empty space, they end up with numbers that are way too big, like astronomically big. So big, in fact, that it doesn't match what we observe in the real world. This huge discrepancy between theory and reality is what's called the vacuum catastrophe. It's like if you tried to count all the money in your wallet, but somehow ended up with $1 trillion instead of just a few bucks. The origins of this problem go back to the early 20th century when physicists were trying to understand how energy works at the quantum level. They started noticing that even in what we thought was empty space, there was still some kind of energy present. This led to the idea of the zero-point energy, which is the lowest possible energy that a quantum mechanical system can have. But when they tried to calculate this energy for the entire universe, it didn't add up. So why does this matter? Well, if empty space has so much energy, then it should be affecting things like gravity and the expansion of the universe. In fact, some theories suggest that this vacuum energy might actually be responsible for dark energy, which is thought to be driving the accelerated expansion of the cosmos. But again, there's a huge gap between what we calculate and what we see in reality. That's why physicists are still trying to figure out exactly how much energy is really in the vacuum, and whether it's even possible to measure it at all. So, you thought empty space was just empty? Think again. In reality, even when you're staring at a blank canvas of nothingness, there's actually a lot going on. Quantum field theory tells us that the vacuum isn't really empty. It's more like a cosmic dance party where particles are constantly popping in and out of existence. It's like if your fridge was full of popcorn, but instead of popping when you open it, these particles pop in and then just as quickly vanish again. This phenomenon is called quantum fluctuations, and it's one of the weirdest things in physics. Imagine you're trying to catch a butterfly that flits around so fast you can't even see it. Except this butterfly isn't made of wings. It's made of particles like electrons, photons, and quarks. They appear for a fraction of a second, then disappear back into the void, leaving no trace behind. It's like your favorite snack disappearing from the kitchen before you can even grab it. But here's the kicker. These quantum fluctuations aren't just random chaos. They actually contribute to something called zero-point energy. Zero-point energy is the lowest possible energy that a quantum mechanical system may have. Even when everything is at absolute zero, there's still some energy left in the vacuum because of all those particles popping in and out of existence. It's like having a tiny battery inside every inch of space, constantly charging itself without anyone noticing. Now, you might be thinking, why should I care about this? Well, scientists believe that zero-point energy could hold the key to some of the biggest mysteries in physics. For example, it's thought to play a role in dark energy, which is what's causing the universe to expand at an accelerating rate. So, even though we can't see or touch these particles, they might be responsible for the very fabric of the cosmos stretching apart. But don't get too excited. This isn't some sci-fi plot where we're about to harness zero-point energy to power our cities. It's still a huge mystery, and scientists are only beginning to understand how much energy is actually stored in this vacuum. Some estimates suggest it could be enough to power the entire universe for billions of years, but we're still trying to figure out how to tap into it without causing a cosmic meltdown. Okay, so you're picturing a universe where everything you know, like rocks, trees, even your cat, is gone. But wait, space is still there. That's the weird part. Space isn't just empty. It's like the fabric of reality itself. If all matter disappears, what happens to gravity? Well, gravity is the force that pulls things together because of mass. Without any mass, gravity would be like a ghost. It's not gone, but it can't do anything. Imagine trying to hold a balloon in your hand without any air. You just can't do it. Gravity would be stuck in a vacuum, unable to exert its usual pull. Now let's talk about light. Light is made up of particles called photons, and they travel through space. But if all matter is gone, does that mean light can't exist? Not exactly. Photons don't need matter to move. They just need space. So even in a universe with no stars or planets, light could still zip around like it's on a never-ending highway. However, without any sources of light like the sun or distant galaxies, there would be absolutely no illumination. It would be pitch black, and not just because there are no stars. There's literally nothing to reflect or emit light. What about other fundamental forces? There's electromagnetism, which is responsible for things like electricity and magnetism. Without any charged particles, which are part of matter, electromagnetism would also lose its grip. Think of it like a game of tug-of-war where all the players suddenly vanish. There's no tension, no movement, just silence. Then there's the strong nuclear force that holds atomic nuclei together and the weak nuclear force involved in radioactive decay. Without any atoms or particles to act on, these forces would be like superheroes without a mission. They'd still exist, but they wouldn't have anything to do. So what happens to time? Time is tied closely to matter and energy through Einstein's theory of relativity. If all matter disappears, the fabric of space-time might start to behave differently. Without mass to curve space, gravity would be gone, and time could either stop or stretch infinitely. It's like if you took a rubber band and stretched it until there was nothing left. It would snap back or just hang in limbo. Time itself becomes an abstract concept without the anchors of matter and energy. And what about dark matter and dark energy? These mysterious components make up most of the universe, but they don't interact with light in the same way as regular matter. If all visible matter vanished, dark matter might still be around, but it wouldn't have anything to pull or push. Dark energy, which is thought to drive the expansion of the universe, would also be affected. Without any mass to influence its behavior, the universe could either collapse or expand forever, depending on how dark energy behaves in a vacuum. Alright, let's dive into a concept so weird it might make your head spin. Empty space isn't actually empty. In fact, it's teeming with energy that we can't see, touch, or even really comprehend. This energy is called vacuum energy, and it's like the universe has this invisible battery that never runs out. But here's the kicker. This energy isn't just sitting there doing nothing. It's actually influencing everything around us, including the very fabric of space-time itself. You might be thinking, wait, if empty space is full of energy, how do we even know about it? Well, scientists have been trying to measure this for decades. They use something called the Casimir effect, which involves placing two metal plates really close together in a vacuum. The idea is that the vacuum energy between the plates is different from the energy outside them, creating a tiny force that pulls the plates toward each other. It's like magic, but with physics and some serious math. Now, here's where things get even more mind-bending. This vacuum energy might be connected to dark energy, which is one of the biggest mysteries in cosmology. Dark energy is what's causing the universe to expand at an accelerating rate, and it's estimated to make up about 68% of the total energy content of the universe. Some theories suggest that dark energy is actually a form of vacuum energy, meaning the empty space we think we know is secretly driving the expansion of the cosmos. But hold on, there's a problem. If vacuum energy is responsible for dark energy, then it should have a specific value based on quantum field theory. However, when scientists calculate this value using their equations, they get a number that's way too large compared to what we observe in the universe. This discrepancy is known as the cosmological constant problem, and it's one of the biggest unsolved puzzles in theoretical physics. So why does this matter? Well, if vacuum energy really is the source of dark energy, then understanding it could help us predict the future of the universe. Will it keep expanding forever, leading to a cold, dark end known as the Big Freeze? Or will it eventually collapse under its own weight in a big crunch? The answer might lie in how we understand this invisible energy that's hiding in plain sight.